please.
Right. Good morning. Let me first thank the organizers for kindly giving me the morning lecture. So I would like to begin to switch a topic from this discussion of the vacuum structure of the of scalar fields or the Higgs potential a little bit towards more dynamics, and then I would like to talk a little bit about models in the last lecture, so tomorrow. But I will do this switch adiabatically. And before I do it, I think that we ended last lecture a little bit abruptly, so we worked so hard to get this effective potential. For some scalar field phi, which was a proper toy model for example, the Higgs boson, the Higgs scalar of the standard model. But I ended a bit abruptly the discussion of symmetry restoration because of time limits, so let's just try to explain what we found without all the derivations that we had. So we were able to see that the effective potential of the field can be split roughly into three pieces. There was the classical contribution to the potential. It had a quantum correction that we could attach to 0-point fluctuations. And then there was a finite temperature correction. That was the result of the fact that the state we often are interested in cosmological applications in particular, is not an empty state. It has fluctuation. It has particles flying around. And we were able to show that this contributes to this function Vt. And for a thermal background, again, the typical situation in cosmology, the distribution functions of particles, phase space distribution function, are thermal. Plus for fermions, minus for bosonic fields. And then in this case, we had an expression for this V of t, Vt of phi. It was just minus the pressure. That is the pressure due to the sum of degrees of freedom in this thermal gas. And maybe the simplest expression we can write is minus a third, just this usual integral for the pressure. Sorry for switching notation occasionally. Well, this energy, omega k, is square root. And I is the degree of freedom we're thinking about. So we derived this, but then we didn't fully kind of consider the results of that. So I wrote an explicit form for this function with the thermal distribution function. It's some integral with logs and whatnot. The way it looks like, however, is interesting. So if I only plot Vt as a function of, for example, phi, and I take into account of the fact that this object is in fact only a function of the combination mi of phi divided by t. Well, for a chiral theory, like most of the degrees of freedom in the standard model, we have, for example, m top of phi in the standard model is some coupling y top times phi over square root of 2. So you see the mass of the particles that contribute to this pressure are just linearly proportional to the value of the scalar field. And our potential is a function of this linear combination. So I can just plot the potential directly, for example, qualitatively as a function of phi. And the shape of it was as follows. At very large values of phi, this thermal potential goes to 0. It goes to 0 because there is a Boltzmann suppression. When you take omega very large, so when you take m as large as you want, it dominates over k for any k. And then this exponential becomes very large. F just becomes e to the minus basically m over t. And this whole object becomes exponentially Boltzmann suppressed. So this potential at very large fields it asymptotes to 0. And at small fields, it goes down like this. And the use of this effective potential, if you remember again, was to define the equation of motion of the scalar field. So if we are looking for an extremum of the field, the extremum is found at the point where d by d phi of v effective of phi equals 0. This was, for example, a minimum for where the field can sit. The full picture for the potential, v is a function of phi. This is just the t part. But if I plot, for example, let me plot the full potential. So let me plot it in pieces. The 0 temperature contribution looked something like this. Then it went up. Then very, very far away it did various stuff, right? There was a 0 temperature instability very far away for the standard model potential. So let's call this yellow line, let's call this V0 plus V1, the 0 temperature part of the potential. On top of that, as far as the equation of motion has to do with stuff, you have to add Vt. So on top of that, you would add Vt, which does something like this. For example, at very high temperature, you have to add this function. Well, this point is proportional to t to the 4, or minus t to the 4. I wrote the expression. I'll write it again in a minute. So what this part of the potential will do, it will decrease effectively, depending on temperature, it will decrease effectively the shape of the potential. So for example, at very high T, this will be V0 plus V1 plus Vt. The shape near the origin of field space at very high temperature will be dominated by this component, and so the total potential will do something like this. If I look at a slightly lower temperature, then this entire object goes up a little bit, and so your potential will do something like this, and so on. And so this is symmetry restoration. This phenomena is known as symmetry restoration because the solution of the minimum equation moves as you go to higher and higher temperature. The solution moves inevitably towards the origin. Phi goes to 0. So that's an important result. Were there questions about this from yesterday? No. OK. So a little point that often comes up in discussions, phenomenological discussion about this behavior, that's the general results. But there might be interest in exactly how this symmetry restoration happens. And there might be interesting dynamics that comes from this. To understand it, it's worthwhile to look carefully at the high temperature expansion and see the exact structure. For example, if this was the plot, for example, for the effective potential for bosonic fields, if I'd made the plot for fermionic fields, it might look a little bit different. Okay, so for example, there would be a little difference in the details on what bosons and fermions would do. This is in the detail. The qualitative behavior is the same, and the symmetry restoration is very generic in this sense. So if I expand the effective potential near the origin, I wrote this last time, so for bosonic field. And fermionic field, the result looks like this. And let me now write one term further. So this was mi of phi squared. And now there is an interesting minus sign. So this was for bosons, and for fermions, you have something similar. So let me write this as plus order m over t to the 4 to the 4. Okay, so this is an expansion. Valid at m over t, much, much smaller than 1. And here is the amusing thing that you can see. For the scalar, or for the bosonic contribution, this term is actually very curious. First, it is curious because this term, when you take into account of the powers, is basically, so it's the 3/2 power of m squared. It looks like m cubed, but it is in fact non-analytic, right? It's the absolute value basically to the power 3/2. So that part is non-analytic, which betrays the fact that the calculation we are doing, it's a one-loop calculation, but it's a calculation to all orders in perturbation theory at one loop. If you were to show the Feynman graphs that contributed to this result, we didn't do it in the path integral formalism, but it is there in my notes, then this effective potential that we are looking at is the sum of graphs with infinitely many vertices that you want. So I remind you, this was minus. This was the full potential. It was minus sum on n, phi to the n, and the endpoint functions to the n. So there were all orders of phi, all orders in the coupling constant. As a result, you get a non-analytic term here. The amusing thing is that the sign of this non-analytic term is actually negative. So now if you consider the phi dependence of this expansion, then the phi dependence on this expansion is there is a constant very near the origin. There is a term that is a constant, so these curves go to the origin flat. As you go farther away, there is a quadratic term, a phi square term, and then there is, for the bosonic case, a negative cubic term and higher order terms. So the result of this is that if you zoom in, well, the result of this is you can think about this equation a little bit more carefully and write what this equation looks like near the origin of field space, near this area. Let's zoom in on this region where high temperature expansion work and see how it looks like. So if I do this, if I zoom in, I can write my effective potential at high temperature effectively as the following thing. It will be m squared plus a t squared phi squared B and A are just names of coefficients that we are going to match to the expansions we are writing. And I'll tell you what they are in a minute. You can read them off directly from the expansion. And I'm just writing a polynomial expansion for this potential. So in here, there would be lambda plus c over 4 phi to the 4 plus higher powers. So we're looking at small fields. We don't care so much about higher powers and the logs and all of this. We are only doing a polynomial expansion. And you can see, for example, this m squared term. There is a t to the 4 m squared over t squared. So all in all, this combination, t to the 4 over t squared, gives you t squared. And from here, there will be a phi squared. So altogether, it looks like we're adding a temperature-dependent mass term. Right? The effective mass of the field has a contribution that looks like t squared. And because the sign of these terms, both for bosonic and fermionic degrees of freedom, is positive, this extra t squared term is always positive. For example, for our phi to the 4 theory, we did this analysis. Our toy model was that v naught of phi was half m squared phi squared plus lambda of the 4 phi to the 4. And to make this structure, we had that m squared was smaller than 0. So spontaneous symmetry breaking, the way we think on it at 0 temperature is Well, you have a negative m squared, you have a positive phi to the 4 term, and you're somewhere in between in the spontaneously broken phase of the theory. But now your negative m squared has a positive contribution proportional to t squared that is effectively stabilizing it. This is why symmetry restoration happens. So you can read off these coefficients. So A, B, and C are just coefficients that you read out by matching to relevant powers of phi in the high temperature expansion of the effective potential. Let me tell you what they are in the standard model, because as usual, the standard model demonstrates everything you want. Yes?
Can you repeat, please, why the term is not analytical?
Yes, because really, if you track what this is absolute value of m squared, basically, to the power of 3/2. So there is a square root in there. The square root is important. So this square root makes this term non-analytic, exactly.
OK. Great, thank you.
So if you take just this term near the origin, you see that it's non-analytic. It's essentially an absolute value. So let's look at the result that you get just in the standard model to understand how this system behaves, right? So now the temperature dependence of this problem, you can track it. These A, B, and C will be constants of the theory, just the coupling, the proportional coupling that enter in all of these terms. You can write for yourselves. And when you change T, it just means that you explicitly change T everywhere here. And then you can see where is the minimum of my field for any given particular temperature. So let's just do this matching for the standard model field theory. So for the standard model, if I take into account the most important degrees of freedom in the standard model, let's match for these coefficients. The most important particles in the plasma are those that have the largest couplings to the Higgs field. The Higgs itself is by far not the most important one, because lambda, the self-coupling, is roughly 0.13. It's very small. The top Yukawa coupling, for example, is almost 1, or about 1. And the gauge couplings in the standard model, so for example, the largest couplings are Y top, which is almost 1. G for the SU2 coupling, which is roughly 0.65 at the scales we care about. G prime for hypercharge, which is roughly 0.36 to my memory. And just to remind, our lambda is roughly 0.13. It is much smaller than the others. And so the degrees of freedom I'm going to count in this contribution are actually not even including the Higgs. You get a good approximation by counting just these. So this is the top quark. It has 12 effective degrees of freedom, as you remember. These with G and G prime are the W plus minus, which has 2 because there is W plus and W minus. So 2 degrees of freedom here times 3 degrees of freedom for the 3 polarizations of each massive field. And then there is the Z, which has 3 degrees of freedom. And the relevant couplings from the standard model. You can read it out from Christoph's lecture. And so here is what you find for A. It's a nice exercise to do, not so hard. You can use all the results from Christoph's lecture to work this out. Okay, so this is exactly coming from your introduction of the standard model. And these mw squared, for example, over v squared is just a nickname, essentially for this gauge coupling squared, for the gauge coupling g squared. Okay, so I write particle masses divided by v. These are just the Yukawa couplings and the gauge couplings. That's what it is. It's just convenient to think on the problem in terms of physical particle masses because of the way that the standard model Higgs sector is built. And I can put the number. Let me put the number. It's one number that is a model independent, right? It's just the result of the standard model. So this is 0.33. Fine. I can do B. B is roughly mw cubed. the B coefficient comes directly from this non-analytic term, and it's only coming from bosonic fields. Okay, the A term was an effective mass term. It came from both bosons and fermions, so we have the bosonic fields and the fermionic fields. But for the B, we only have the bosonic fields, because only bosonic fields have this non-analytic contribution. And this is something like 0.03. Fine, so we do, in fact, have a tiny little cubic coefficient here. And the C is less important and more complicated. So I just write the leading contribution is from the top. There is a number here, T squared. So this C coefficient has a logarithmic sensitivity to temperature. That's not very important for us. The leading sensitivity to temperature is power law. That's a very small sensitivity. 16 pi squared v to the 4, plus things from the W and the Z that are less important. And that's not very important. This is minus 0.05 at a temperature of around 100 GeV. So there is a small logarithmic sensitivity to temperature at the one loop order that we are working at. So I can just work out. The theory tells me, yeah? Sorry?
How do you get to those values of A, B, and C?
Okay, you go to this expression of the effective potential.
Yes.
And you simply insert the values of the masses, or the expressions for the masses, m as a function of phi. So for example, again, for the top quark, to work out, for example, if you want to work out the contribution of the top to these things, then you will write that m top is y top phi over square root of 2.
Yes.
This is the top. It's a fermion. It has a factor of 12, so I should put, let's call it GI, just number of degrees of freedom. Just count how many independent, effective, real propagating degrees of freedom they are. As we said, for the top, G top is 12. Minus signs are already included here, so here there is no minus sign for the fermion. It's already included in the calculation. It's just the pressure. Pressure is pressure. So take this value of mt, plug it inside of the expression for the m squared. Notice that the t squared cancels with this t to the 4, gives you overall something that looks like y top squared times t squared times phi squared. And so you see there is a t squared times phi squared, and you can read out the value of A. Okay. So that's the trick. Check me if I screwed up some factor of 2 in my expression. I think I didn't. But that's all there is to it. Okay. And same for the other particles. More questions?
Thank you.
Yes.
How does new interactions appear in these parameters? I mean, if I introduce a new particle or a new sector, I will have a new coupling with the Higgs. How would they have the contribution present in these parameters?
Great. The question is, if I add more particles that couple to the Higgs, how would it change this picture? It's a very good question, and the answer is very easy to make. So the answer is very simple. Take your new particle and calculate its mass. So mass of new physics as a function of the Higgs field. For example, if you added another quark with a different Yukawa coupling and some contribution to its mass from the Higgs, it will have a contribution to this particle mass. Now go ahead and simply plug the expression that you found for the particle mass inside of this expansion at high temperature. And that's it. You can read off in exactly the same way the contribution to A, B, and C, and there will be indeed a contribution to A, B, and C.
Okay, and you did the assumption that we are working with a real field. Well, for the scalar fields, this is not an assumption. You can always do it. Okay, but now we're going to the Higgs, that is a complex field. Yes, the Higgs is complex. Great question, and a general question, right? So the question in general is, but I will finish this, and then please remind me to go back to your question and clarify it if I forget. I'll try to not forget as well. But so the question was quite general. The question was as follows. In all my discussion of the effective potential at 0 temperature, finite temperature, whatnot, I was thinking about a single real scalar field degree of freedom. But often in life, you would find complex valued scalar fields, right? For example, the Higgs field in the standard model is more than complex. It's an SE2 doublet. So in fact,
It has two complex components, the upper spin and the lower spin, kind of in the spinor representation of SU2, yes? So, or isospin representation. So it's actually two complex degrees of freedom. How do I connect my toy model of real fields and all this formalism when my field is actually complex and not real? The answer to this is simple, and I'll get to it in a minute. The short answer is, for scalar fields, you can always take any complex representation or any complex structure of the scalar field, simply split it into the real and imaginary component with I in front of the imaginary. You have a collection of real fields now. And so now work out the exercise. They are all coupled to each other by virtue of the Lagrangian that couples them. There might be some symmetries. You might want to choose a basis between them. But in the end of the day, you always go down to discuss a set of real fields. So first step, complex fields is not a problem. Internal global symmetries like SU2, not a problem at all, because it's simply a list, in the case of the Higgs, of 4 real degrees of freedom, right? 2 complex components of the isospin break down into 4. Each one of them is 2 real components, the real and imaginary part. So 4 real degrees of freedom. You can write it as a 4-component vector of real fields. And then the one non-trivial generalization of what we're doing is that, in principle, I was working on a scalar potential that has 1 field direction, but in real life, there might be more field directions to this object. Then you have a slight technical issue there, because the structure might be non-trivial in all of these field directions. Formally, it's quite easy. What you do, you can just now generalize this to the potential as a function of this landscape of fields, or different dimensions in field space, increase all the masses of these particles in the theory, both for the 0 temperature expansion and the finite temperature expansion, as a function of the scalar field values in all directions, and you get essentially your expression. So now you have a scalar function V that's a function of multiple, right? It's now a function on Rn if you have n scalar degrees of freedom. Okay, so I answered, I think. So that's the answer. It's a bit more complicated. It's now a manifold. It has more directions to go.
If a particle is uncoupled to the Higgs, does it also contribute to this potential, to this thermal potential?
Necessarily, yes. If a particle is coupled to the Higgs, it will contribute. And it will contribute to the 0 temperature and to the finite temperature. In both cases, our calculation is very simple. All you have to do is find out the relation between the effective mass of your particle and the value of the scalar field. And so that's the only object you want to compute. That's the only object that goes into the 0 temperature potential, and that's the only object that goes into the finite temperature potential. Just go ahead, take this, and plug it into the expression, and you're done. So that's the only thing you need. Of course, if your particle is very, very massive compared to the rest of the particles, so for example, suppose that my particle, M nu physics, has a contribution that looks like, let's make it squared, big M squared plus some coupling, let's call it kappa phi squared, for example. Very good, I can just go ahead and plug it everywhere. If M is very, very large compared to the rest of the particles and large compared to the temperature, the contribution to the pressure from this thing is Boltzmann suppressed, and you can forget about it. It will be a small contribution. It will contribute to the 0 temperature potential and so on. And if big M is small, it will contribute more in principle. So you can study this. There will be decoupling properties like you expect. Everything will behave as you expect.
Okay, so it contributes to the potential even if it's not coupled to the Higgs? Or?
Oh, maybe I missed the question.
Yeah.
The question was, what happens if it is not coupled?
If it is not coupled, yeah.
Okay, sorry. What happens if the particle is not directly coupled to the Higgs?
Yeah.
Okay, everything we've done here is effectively a one-loop approximation to the effective 0 temperature and finite temperature potential. At one loop, you will contribute directly only if you have a direct coupling. You would contribute only if you have a direct coupling to the Higgs. Now, when you look at this a bit more carefully, something that I didn't fully do, especially the 0 temperature effective potential, when you look at very large field space, you care about the renormalization group evolution of coupling constants. I did not derive this for you, but it is in my notes in full, okay? this discussion. So how do you deal with the zero temperature now? I'm talking about the yellow one. How do you deal with the effective potential at very, very large field values? There you have to worry about renormalization group evolution. It is possible that your new degree of freedom contributes to the renormalization group evolution of the coupling constants of the particles that do couple directly to the Higgs. Okay. Then it will play a role. Okay. In the standard model, this really does happen. In the standard model, for example, again, the top quark Yukawa is the leading, the most dominant direct effect why we have this instability. Fermions tend to destabilize the Higgs potential. But the top quark Yukawa itself runs to become smaller. It has renormalization group evolution. It becomes smaller at very large renormalization scale mu because of gluon interaction, because of QCD. So in fact, if you want to understand this structure, you need to solve renormalization group evolution, including G strong, which does not couple directly to the Higgs. So that's a great example. Okay. And it does play a rather significant role, certainly a two-loop for the standard model. So that's the short answer. All the expression I'm giving you here are explicitly one loop, so you won't see it.
Okay, thank you.
Okay, thanks for the questions. Let's go on exploring the consequences of these numbers and these expressions for the standard model, because you see what happened is we found some non-trivial value for A, you'll always have it, some non-trivial value for B, and C is much less important. I can essentially forget about it. You see this C 0.05 compared to, remind you, to lambda, which is 0.13, that's a relatively small correction. So here C comes together with lambda, we can more or less forget about it. It's not very important. But this is important and this is important. So what I want to do is really, I want to change, to zoom in on this region of small fields and change T and ask just how this polynomial looks like. So I can erase this. Well, as you go to smaller and smaller field values, let's zoom in really close to the origin and change the value of the temperature. If I look at very small phi, I'm allowed to do it, why not? Then at very small phi, the phi to the 4 is much less important than phi squared, and the phi cubed is much less important than the phi squared. And the main thing you want to care about is this object here. And then the zoom in, V effective, as a function of phi, at 0 temperature, our potential looks like this. Oops. Our A term is some number, but T equals 0, and so our potential is just this thing. It has a negative slope near the origin. Now what happens when I crank T up, further up and up? What will happen is my effective mass term, m squared plus 8t squared, which is minus m squared plus 8t squared, because m squared is smaller than 0, this approaches 0. Let me, to avoid shifting up and down my potential all the time, let me just add a constant whenever I change t, so that I'm going to, let me fix, who do I want to fix? I want to just look at the shape of this thing as a function of temperature. Yes, in fact, why don't I add a constant to this object? I just want to ask what is the dependence on phi. Let me add a constant. So the potential is always clipped to 0 at phi equals 0. Okay, I hope this is clear. So this is the situation at t equals 0, and this is the effective potential plus a constant that depends on t. I can add the constant because I just care about the question, where is the minimum? That's the only thing I want. So at 0 temperature, I'm here. Then as I increase A, or as I increase T, this object is going to move, and it's going to do something like this. This is some T larger than 0. Okay, my coefficient, this is something larger than 0, but still such that the sum m squared plus at squared is negative. I still have a drop down, a roll-off here with negative mass, but it's closer to 0 than it was before. Then I increase t a little bit more. Let's call this t1. I will get here. If I increase t even more, there will come a moment in life where this combination is 0. When this combination is 0, what happened is the origin has been stabilized. So this is T2 larger than T1, T3 larger than T2, okay, going up in temperature. There will come a critical moment when the origin is stabilized. At what temperature do we get this critical moment that the origin is stabilized? Now suddenly the minimum of the solution lives here. At 0 temperature, the minimum was here. Okay, so somehow our minimum needs to travel and eventually reach this point at a special time. Okay, when does this happen? How did I call this temperature? Well, to make life nice, I call this temperature T naught. So let's call it T critical. There will be a critical temperature when that is equal, so T critical squared is minus m squared over a. At this temperature, dV effective by d phi at phi goes to 0 becomes the global minimum in this region. Okay? This is the temperature that you would roughly associate to this phenomenon of symmetry restoration. At a smaller temperature than this, the minimum is somewhere further to the right. At a larger temperature, the potential will just go on increasing when T goes on, and the origin remains stabilized. So for the standard model, we can just work it out. For the standard model, m squared is just a number. We know that the mass of the Higgs in the standard model, mh squared, is minus 2 m squared parameter, which is 125 GeV squared. So the standard model actually, once we calculated this A number, which I calculated here, I can tell you what is the critical temperature for the standard model. And the answer is roughly 150 or 154 GeV squared. So at a temperature of around 150 GeV, the standard model, actually the minimum is at a symmetric phase. SU2 and cos U1 hypercharge are not broken. Questions? So for the discussion that we had about cosmological constant, and I had some comments about this, and so if people have comments or if somebody thinks that I'm misinterpreting what is happening, go ahead. What is happening for us? Suppose for a minute that this evolution of temperature is slow and adiabatic compared to particle timescales. In that case, our field would locally track this evolution, okay? Now, if I put an arrow of time on this, of course, arrow of time in the Big Bang is the opposite, right? We are going in this direction in terms of the vacuum expectation value of the field. We are stuck here for a long time in a symmetric phase. We don't move at very high temperature, but then suddenly we begin to roll down. And so if you look at the cosmological constant part, the vacuum energy part, coming from the scalar field, then it has this gap. For a long range of temperatures, all the higher temperatures higher than Tc, the scalar field is effectively stuck here to a very good approximation. And so the cosmological constant component of this part of the potential is there is a rho lambda that is essentially V of 0. Then the field begins to roll. For a while, it is rolling together with temperature, so it is evolving. In fact, at the time that it is slowly moving, the equation of state or the behavior of the theory is slightly different than a pure cosmological constant. But then eventually, it will settle somewhere near here. When temperature effects becomes negligible, Eventually, temperature becomes so small that you can neglect it compared to the bare parameters of the theory. And then at temperatures that are even smaller and smaller and smaller, you see that this curve is just going to merge with the zero temperature curve and stay there. And for the electroweak theory, for all intents and purposes, you're basically stuck to the zero temperature potential below a few GeV of temperature. You're basically stuck here. You're not moving anywhere, not much. And then you have, in this region, a cosmological constant that is V of phi c, or V of 246 GeV. We worked this out. This jump is of the order of 10 to the 50 giga-electron volt. And so to the 4, right? So 10 to the 50 GeV to the 4, roughly. This is this jump in cosmological constant that we have. So scalar fields, for a while, there is a cosmological constant. Then it evolves. It is something else. We'll discuss what it is. And then it settles on what it is today, an infinitesimal fraction above 0, as we know from vacuum energy measurement. OK, so that's the critical temperature. Let's zoom in even a little bit more on the fine detail of what is happening here. Any question about this? Yes?
When the universe passes through this stuff, I mean, it is a cross-phase transition, right? And how does it happen? I mean, the phase changes the entire universe at once?
So the naive picture of this, which is the picture I more or less think I understand, is indeed that on causally connected patches of the universe, this transition, you can think of it as homogeneously, as slow adiabatic change of this symmetry restoration parameter, basically of the VEV. So the VEV slowly transits, and it does it homogeneously everywhere at the same time, moving on time slices.
OK.
Yes. This is in the case of a second-order phase transition. If this transition is very smooth, let's ask what it is in the standard model, because when you look at the fine details here, you see when you get to TC, the quadratic part, by definition, vanishes. When the quadratic part vanishes, you want to be careful about the next terms. Yes?
I have a question about the value of the cosmological constant as the temperature decreases. I mean, the value is we know that it's very fine-tuned, right? So even if the temperature, it has to have this very specific value, so even if the temperature...
I'm not sure I understood the question. So you suggest the cosmological constant is fine-tuned?
No, it's because essentially the cosmological constant in the beginning of the universe is like 10 to the 50 GeV, and
compared
now,
to what it is today, yes.
And now it is several orders of magnitude below that nowadays. And so is there a time, there will be a time in which very small changes in temperature will lead to orders of magnitude of change in the cosmological constant? Well, does this model actually say that?
It's not exactly, if I understand the question properly. So, there would be a time where this order parameter, the value of V, and therefore the value of the, if you want, the value of the scalar, the potential contribution to the energy density coming from phi, right? V is just the potential contribution to the energy density coming from phi. There are also kinetic terms. Kinetic terms are 0 when you're literally stuck. So when you're literally stuck, all you have is this constant, and it acts like a cosmological constant. When you're moving, kinetic terms are not exactly 0. So the details of what you're doing here could change the interpretation. If this object is varying, it is not literally varying in time. It's varying in temperature, so it's varying in time. Then this object is not, strictly speaking, you cannot, strictly speaking, classify it as a cosmological constant. Okay. It is what it is, a contribution to the energy momentum tensor of the system. It's effectively the same as cosmological constant here and here, but here it's some...
Yeah, but I mean, when the temperature corrections make it so that the potential is barely grazing the temperature is equal to 0.
This part.
Yeah, like when the temperature is just above.
Good question, but so the thing is, as I said, the system stabilizes just a little bit after 100 GeV. After that, the change, you can compute the change. You can still try to do this expansion and ask what is happening, or you should use the full function when you go to smaller temperature. And you will see that you approach very fast the 0 temperature result. So you have a small, very small contribution. Yes, the cosmological constant, when it kind of gets near to the final result, it is changing. Yeah. Even the small change is a lot. However, at the time that it is changing, keep in mind that in the background there is all this radiation energy density that is by far dominant. So as far as gravitation is concerned, as far as the Hubble constant, for example, is concerned, this system, when it is still settling, is by far radiation dominated and later matter dominated. You know, we have become cosmological constant dominated only very recently, redshift of something like 0.3. Very recently, a few giga-years ago. Until then, it was dark matter dominated. And so the Hubble parameter, for example, cared very little about that, if you want. Okay, so you are right.
If it had happened today, then it would be very noticeable.
If it was still adjusting today, maybe it is by some other field direction still adjusting today, then you could potentially see it. Maybe this is what Desi and Des think that they're seeing, the statement that maybe there is a time independence of cosmological constant. Could be something like that, for example, naively. Yes. Okay. But for this system, the standard model, it will be very small.
OK, thank you.
So I want to zoom in even more on this region to spot something interesting. If we only had phi squared and phi to the 4 term, then when I zoom in the picture, so for example, suppose that you have a system that has only bosonic degrees of freedom. In a system with only bosonic degrees of system, with only fermionic degrees of system, this B is 0, okay? Or very, very tiny. In a system like this, I only have the phi squared and the phi to the 4 temperature corrections. The phi to the 4 is a positive stabilizing effect. The phi squared does the behavior that we wanted. So in a system that has only, I can write it like this. Let's make 2 copies of our life. This is only fermions in VT. And this is, in principle, fermions plus bosons. Okay? How does the potential look like? Close to the critical temperature. For the system with only fermions, you have your destabilization at 0 temperature. And then as the temperature goes up, we have our curves that are doing this. Then they go flat. At the point where the curve is flat, it's just a pure phi to the 4, and so there is a massless degree of freedom there. You want to be a bit careful about it, but there is no extra structure. The origin is flat, and then the origin goes up. This is a zoom in of a system where the pressure is only from fermions. In a system where the pressure is from fermions and bosons, B is necessarily not 0. And so where we are, T equals 0, and T goes up like this, the system gets stabilized towards symmetry restoration. But then if you zoom in very close to the origin, at the point where the origin is stabilized, in fact, if you go a little bit after that, suppose you go to the point where A is a tiny bit larger, AT squared, tiny bit larger than M squared. Now the origin has a positive curve, very near the origin. However, when you go a little bit further away, necessarily the cubic term would dominate, right? And the cubic term is always negative for these simple systems. So the cubic term has a negative sign. And so the cubic term is going to bring you down. And for a little brief interval of time, you're going to be in a structure like this. Then later on, it will do something like this and stabilize completely as you go to high T. So the interesting point is that if the system has bosonic degrees of freedom, there will come a time where there is now suddenly a local minimum at the origin, but another one far away from the origin. And interestingly, they are actually separated by a barrier. In this case, you might think that there can be, just like in statistical mechanics, there can be first-order phase transitions. Now you have, this is our free energy. It has two minima. And suppose that we are somewhere here. Why are we here? Because the way time works is time comes from the top curves to the bottom. So naturally, time will put our systems in the origin. Then temperature will go down. And suddenly, you should think about it as time progresses, temperature decreases, and suddenly a remote minimum appears separated by a barrier. This is necessarily the case when you have bosonic fields and you're thinking about this one-loop calculation. And then you might have first-order phase transitions and this bubble nucleation and so on. Many people are working on models like that. And so in the standard model, this is in fact, in a way, at least the one-loop naive, one-loop perturbative calculation suggests that this is the situation that we are at. So let's zoom in on this. Could it be that in the standard model, we actually have violent first-order phase transitions around 150 giga-electron volt? If we do, this is crazy. We can try to look for gravitational waves and whatnot. There's been a huge amount of discussion of this story. So what can we do about this? Spoiler, the answer is no. Not about what can we do, but about is this the situation? In fact, as I will show you, you need to be careful when you try to think about a very small field region. And you need to ask yourself, is this one-loop perturbative calculation really, really trustable, okay? So, but naively in the standard model, that's the picture. So to understand this picture, it's enough to think about this polynomial potential, right, at very small fields and a temperature that is very near to critical. And so you can ask yourself, let's define a temperature. Let's call this temperature T, I don't know, phase transition, supposedly. Again, be careful. It's not going to be an actual phase transition, but let's call it like that. And let's define this Tp as the temperature where the remote vacuum forms at the first time. So this will be Tp. And it's exactly degenerate with where we are. After it forms, a moment later, it will be energetically favorable, and you could think that you can try to tunnel to the other side, yes? So the critical temperature or a noteworthy scale is this point, where they're exactly degenerate. And you can work out what it is just by analyzing this simple polynomial. And the answer is this. This is roughly. When you do this, you can remember that the quadratic term is nearly 0. And all terms are, in fact, of equal contribution. So you can write, this comes to be the following. OK, let me first start with this. So that's the expression when you analyze, just ask for the minima to be degenerate of this polynomial. But now in the standard, this is 9, this is B. Yes, and you have to have B not 0 for this Tp to be different than Tc. If B is 0, if the cubic term is 0, then in fact, this point in life is just degenerate with the point where the quadratic term just vanishes, right? It becomes the same. There is a degeneracy between these points. It becomes an inflection point. Good, so that's the expression, but in the standard model, we can write what it is, because we have all these numbers. And the answer is 1.004 Tc squared. Okay, so this time appears, it's predicted to appear. It is such a tiny, so the standard model has such a tiny B term, you see? I wrote it over here. It's so small, it's only coming from the gauge bosons. compared to the other contributions that include the top, for example, and the bare mass parameters, it is so small that numerically this coincidence is predicted to appear, but it's extremely close to where TC is. So you make it, but a very slight moment after it, the barrier basically disappears and you become unstable. Okay? So does the standard model have a first-order phase transitions or not? Naively, it does, and we can be excited. How should we think about it? There are several ways that you can think about it. But so this is, for me, a general cautionary comment about thinking about these thermal potentials and what you can do with them. So TP, very, very, let's call it subtle. Nearly TC. And you can be worried that it is so close to TC that this is an artifact of perturbation theory. How would you check it? So one thing that you can do to check it, you can ask, OK, if there really is an effect, this effect is because of what? This effect is because my order parameter, the excitement is about the possibility that my order parameter, the scalar vacuum expectation value, would jump discontinuously by bubble nucleation to the far side. And so you can ask yourself, what is the size delta phi of this jump? And one natural thing that you can compare this size to, as a first check if your calculation makes any sense, there is already some uncertainty in this calculation, physical uncertainty, coming from the fact that we are talking about a thermal system. If you visit different parts of it, you will find inevitably thermal fluctuations on top of it. And in fact, these thermal fluctuations were crucial to deriving this entire phenomena. So as a check, compare the jump with the thermal fluctuations. And recall, here is, we actually computed them. We computed the expectation value of phi squared, var phi squared. Var phi squared, var phi was exactly the thermal fluctuations in this case. The thermal contribution to phi squared was the thermal fluctuation on top of our field. Remember, our field was defined as phi c plus var phi. And the thermal fluctuations we computed, in fact, in this theory. So you cannot really separate var phi from phi c, for example. How do you measure phi c if you go to some point and ask, do I want to make a bubble or not at this point? When you go to visit the point, it will be messed up with some thermal fluctuations. Only on average, it will give you phi c. And phi squared average is the RMS. If you take the square root, d phi, let's call it d phi thermal, it will give you some uncertainty. Let me mark it like that. So here near the origin, there is some fuzziness, if you want, to our entire calculation. And the size of it is roughly delta phi thermal. Let's compute it. We can actually compute it easily. Our calculation included this computation. So we have to compare two things. We have to ask ourselves, how does delta phi look like in comparison to the square root of the average of phi squared, which is delta phi thermal? And we have this question mark that we want to answer. So let's call this delta phi p. It's a delta phi related to this exact jump, delta phi p. That one is very easy to calculate. That is just coming again from the polynomial. And so it's trivial. I'll let you do it. And this delta phi p is roughly b over 36 Tc. Again, notice it becomes very small, this jump, if the b parameter is very small, if you don't have a negative cubic term. Fine, very good. So you can put the numbers yourself. It's a tiny number. Let's compute this thing. So why don't I literally compute this? So you remember that, let's compute this object. So remember that d by d phi of m phi squared of phi times half phi squared. This was exactly d by d phi over vt. This is how we did the derivation. That's all you need to calculate. Just evaluate both sides of this expression. For the 100th time, this is m squared plus 3 lambda phi c squared. So we can calculate the left-hand side. The left-hand side is equal to, I'll do it here. This is just a half, and d by d phi of this object is just 6 lambda m phi, right? So this is 3 lambda phi c phi squared. So that's the left-hand side. We did it. It's depending on phi squared. The right-hand side is the d by d phi of vt, which I wrote many times before. So this is t to the 4. There is a constant part that doesn't matter. And there is the usual part that does matter. Plus other terms. So the constant part drops when you take the derivative. You again have just a derivative of m phi squared, which is what I did before. And so on the right, what I find is 3 phi c t squared over 4. So the thing here on the far right needs to be equal to the thing here on the far left. This is usually the case. If you go far enough to the right, you find yourself in the far left. Remember that. It's good for politics. So I can equate these things. And I can write that phi squared, let's see. OK, so the lambda phi c cancel. Let me cancel them on both sides. And I have a 4 and a 3. So this is equal to t squared over 12, a relatively famous result for the thermal fluctuations of this object. In general, if I had added additional degrees of freedom to the thermal potential, as I should, there would be a slightly different coefficient, because other fields can contribute. But this is good enough for us. Now our question is very easy. Our question is, how does this delta phi compare to the square root of phi tilde? I shouldn't. I am. I canceled the phi c by accident. Thanks. I was missing a lambda. So there is no lambda here. And now my question is delta phi p, which is b over 39 tc, and I have delta phi t.
Sorry, it's over 12 because it should be
there was a 4 here.
A 4, yeah, and a 3.
There was not a 3.
Okay, yeah.
I was missing a lambda and I had an extra 3. Thanks a lot. But do this exercise. I mean, it's just a derivative of the function that we had. And delta phi t, I can put a tilde, was roughly tc over 12. You immediately see that delta phi p is much, much smaller than this delta phi thermal. So this naive one-loop expectation of all this subtle structure, you know, the barrier and this little extra point, this is at Tc for the standard model, completely buried inside of this thermal phase, which is a strong alarm bell for us. It tells us that this exercise is very sensitive. This question of the phase transition is very sensitive to what is happening near the origin of thermal fluctuation. And in fact, indeed, when you investigate it, you see this one-loop calculation at very small fields at that temperature cannot be trusted, and there is not a first-order phase transition, and there is, in fact, not a barrier in the standard model. Calculation is complicated to resolve these small details, but it's now established that there is not this structure. The general structure of symmetry restoration is much more resilient than these details, and it is there. It's robust to these details and occurs in the standard model. Okay. I think this is all I wanted to say about the symmetry restoration now. More questions, or should we go on?
If I understood well, radiation is still dominated in this phase, right?
Yes, at 100 temperatures of order 100 gigaelectron volt, we can calculate it if you want. So the radiation, actually, it's very easy to compute. Good question. What is the dominant energy density at 100 gigaelectron volt? This is easy. I will do just a rough estimate. The energy density because of phi, just because of the potential of phi, is very roughly of the order of lambda phi to the 4. So let's do this exercise near the broken phase still, okay, after you break. So this is very roughly 0.1 times 100 gigaelectron volt to the 4, give or take a factor of few. The radiation energy density is of order the number of degrees of freedom of all the particles in the plasma times T to the 4. And so again, near this temperature of 100 GeV, it's the number of degrees of freedom times 100 gigaelectron volt to the 4, but the number of degrees of freedom is of order 100. So when this entire interesting story is happening, at the time that it is happening, in fact, the radiation energy density is a factor of about 1,000, very roughly higher than all of these movements of the scalar potential. It's a tiny sub% perturbation to the total energy.
Yeah, I was wondering exactly about that. How could this fit into this scenario? Since you said that it is a fuzziness, fuzziness, right?
Fuzziness,
yeah.
Yes.
Then I was trying to picture that in the sense of this evolving system, because then I was wondering about CMB and this relation and maybe anisotropies. I don't know if this has connections with that too.
So it's an excellent question. Can we see it more in general? But the short answer is that unfortunately 100 gigaelectron volt, while this dance is happening, is way, way early than CMB. This is the times that are a fraction of a nanosecond in the FRW age of the universe. CMB is happening at hundreds of thousands of years. So way, way, way later in the evolution of the universe. In terms of scale factor, this is happening at a scale factor of 10 to the, so BBN is a scale factor of 10 to the 10, Z 10 to the 10, and that's roughly at 1 MeV. That's another factor of, so this is redshift of 10 to the 15. That's when this thing is happening. And it's completely obscured from us by the plasma of the standard model itself. So if there was a first-order phase transition, gravitational waves from it could, in principle, reach us today. But no electromagnetic signature or any chemistry can actually, or another thing, if there was a first-order phase transition, maybe it could do something with baryon asymmetry, and that could reach us today as well. So there are many, many works on that. In the standard model alone, there doesn't seem to be any, violent dynamics going on anyway. So, but other than that, setting the baryon asymmetry and maybe gravitational waves, it would be very hard to see what is happening.
Okay, thanks.
Yes, and during the time of CMB decoupling again, excellent, so maybe that's your point, there is still a thermal fuzziness. So even today, there is a little bit of thermal fuzz, but it is absolutely tiny. You can compute it, what it is compared to V. Okay. So I would like to start to talk about other things that scalar fields can do. Because
Professor.
there is another question? Ah, yes.
It's me again, sorry.
Sure. I appreciate it.
You wrote the values for the mass, for the couplings and stuff like that, but we have some uncertainty in these values, right?
Say it again?
Uncertainty in the values of the mass of the top, on the bottom.
You mean experimental uncertainty today?
Yes.
Sure.
If I push the values in the error bar, can I have a first of phase transition?
We are way, way off the first order phase transition. So you see what we had, if you want, let's just look at our naive check. Our naive check was asking about delta P, which was roughly B over 39 TC. Let's divide delta P by delta T. That's kind of the check that we did. So it was this divided by TC over 12, very roughly. So the TC cancels, and there's something like 12 over 39 B, which is like B over 3, which is, something like 0.001. Much, much smaller, a factor of, for our calculation to have been potentially reliable, this ratio should have been larger than 1. We are off by a factor of 1,000. Changing the little uncertainty on the value of the couplings of the standard model would change this result. It would change B by today by percents.
Okay.
So this story seems to be gone for the standard model.
Okay, great. Thank you.
However, for many years, mostly before the LHC, people have played with the possibility of indeed adding more particles to the plasma in hope that they would trigger a strong first order phase transition. Sometimes people are still toying with this. In principle, you can try to do it. A notable example that people have looked at here at our supersymmetric partners of the top, the stops. And why stops? Why supersymmetric top? Because they essentially inherit a Yukawa coupling of the top that is already very big. And that we wanted them, in a way, we wanted them to be light because they are part of the fine-tuning problem for the Higgs mass. So that was kind of a merging of causes. The stops being light and having a big Yukawa could, in principle, allow them to play in this game. They are scalar fields. They are scalar partners of the top. And they could, in principle, increase B. And in some region of the parameter space, for a while, people thought they could trigger a strong phase order phase transition. However, this game is tightly constrained because, again, you need the scalar particles. You need them to be significantly coupled to the Higgs and very light. Not light, they would be Boltzmann suppressed, right? Not coupled, they won't do anything. So light and significantly coupled, that is exactly the stuff that the LHC was looking for, right? So we haven't found them. And so this picture becomes very constrained. Okay. So next week, you will hear a lot about models of dark matter. Nicholas, I think, is here. Will tell you about models of dark matter and issues related to dark matter. And in fact, what I wanted to do now, since I spent so much of your time thinking about scalar fields, why don't I try to make a connection between the cosmological dynamics of scalar fields to dark matter, which is a relatively hot topic today. Many people are thinking about it. You shouldn't care what many people are thinking about, but that's just a fact. It will affect the papers you read. But it is an interesting possibility for scalar fields like this are actually interesting possibilities for dark matter. And I think Nicholas will not talk about them at all. And so we already see, when we ask about the standard model, we see that these scalar fields can have and do have non-trivial cosmological behavior. Even the simple modest Higgs of the standard model moves around during cosmological history. For a while, when it's moving around, it's not playing the role of a cosmological constant. It's doing something else. And so it's interesting to ask in general, what does a scalar field do cosmologically? And so I want to ask exactly this, the cosmological dynamics of a scalar field. I will do this analysis classically. And you have the tools to extend it with the thermal and quantum corrections when you want, at least when the theory is perturbative. Okay. So, and then I will connect it tomorrow to a particular model that is interesting, the axion. Oh, I have 10 minutes. Nice. Cosmological dynamics of scalar fields. So we've just talked about the vacuum structure of scalar fields. V is the function for phi. And now I'm not thinking about the Higgs anymore. I'm increasing the scope a little bit. Some arbitrary scalar field with some potential that, as we've seen, can be a rather interesting function. And as far as cosmology goes, Big Bang cosmology, well, in radiation-dominated or matter-dominated regime before, if you don't consider inflation, it actually has an origin of time. Let's think about it in this sense. Let's think about the story since the hot Big Bang started. Then there is an origin of time. There is a zero of FRW time. And in a way, you know, the director says, cut, or the opposite of cut. What's the opposite of cut? And action. And the film is rolling. Of course, in the picture of inflation, we think there is an earlier time, but it's not going to be crucial for us. In fact, you will see. And so in this kind of perspective of action, you can ask yourself, we've talked about the fact that the equation of motion has stable solutions at minimum of the potential. But why would it be the case when the director says action that the scalar field is here? In general, the scalar field could be anywhere. Why can't it sit anywhere you want on this potential? We don't know where it will sit, right? It's just some state variable here telling you where you are. And so the question is, when the director says action, where are you going to go? You know where you're going to go, but how are you going to do it and what are you going to do? Of course, inflation itself, incarnations of inflation models are asking questions like that. I'm not going to go in this direction, although it's really fun. I will start thinking on this problem when my scalar field is actually not the dominant contribution of the energy density of the universe. That's essentially the difference between what I'm doing and models of inflation. Let's start with a radiation-dominated universe and some scalar field stuck somewhere. For example, for the Higgs we just saw, the Higgs starts at 0, actually, because of thermal effects. And it's by far a very tiny contribution to the total energy density. And then as temperature decreases, the Higgs actually, it starts here at the top of the hill for a reason, the thermal reason we more or less understand, and then begins to roll. So here is again a non-trivial example. I'll think about something like that. And I'm thinking about the cosmological dynamics and the classical dynamics of it. And so the first thing to start with is to find an energy momentum tensor of this field and find the equation of motion and solve it. I will do this very quickly in just a few minutes. And so I will think about the dynamics coupled to an expanding universe. That's also a bit new compared to what I did before. I was just thinking about the scalar structure itself. So I will think on the action of the problem as a function of the field phi and the metric. In principle, there are additional fields that you can add. Now you know how to do them, to add them, but I'm not going to care about them so much. So what is the relevant action that I have for a scalar field? The GR form is this. Minimally coupled. And I'm going to add here also gravity, where R is the Ricci scalar. I'm not going to use this much. Again, really using this will mean inflation. So in principle, there is an additional contribution to the matter. This is the potential you know and love. This is just the kinetic term. And I will mostly work in the homogeneous and isotropic limit of the background of the space-time. In this limit, my G mu nu is just the FRW one, so ds squared in the comoving coordinates you know, which means this is G mu nu, dx nu. So my G mu nu can just be read, and also my conventions, and it's that. And other things that are appearing in these equations are, for example, square root minus g, which is just the absolute value of the determinant of g mu nu. Because of my signature, the minus just takes care of the minus sign, right? Because there is the product of 3 minuses, and I want the whole thing to be positive. And so, and square root. And so this is the square root of a to the 6. So this is a cubed. Okay, these are the objects that are appearing in this equation of motion. And the first thing you do when you're handed this kind of action is to find the energy momentum tensor. For those who haven't played with this, there is a trick to find the energy momentum tensor. Which is, you go ahead and you take this functional of g mu nu and of phi, and you just take the derivative. So energy momentum tensor of the field, let's call it T phi mu nu. So that's an exercise for you. Take the variation derivative of this object with respect to g mu nu of the matter part over the phi field in particular. Again, you can see these details, I think, in my notes. If you don't find them, I'll give it to you. Because I'm not 100% sure if I put them there or not. So this is, if you do this exercise, this is what you're going to find. So you take the variational derivative, or the variation in this case, I keep the integral. And after some integration by part, you can bring this result to the following form. And the object in front of this prefactor is going to be the scalar or the matter energy momentum tensor. And of course, you want to check that this makes sense. So to check that this makes sense, the second part of your exercise is to derive the Einstein equations. So as the second part of your exercise, notice that the total derivative of the total S, you see this action roughly splits into, let's call this part, including the integral SGR, and let's call this part including the integral S phi. In this sense, the action splits into S phi and SGR, and S is just the sum. So if you take the derivative of this with respect to, of SGR with respect to g mu nu, then this is the g mu nu. Minus g of r. You have to work a little bit, but after you work, you find this. Delta g mu nu. And so you will find that the coefficient, if you take the derivative delta g mu nu of the total S and set it to 0, you will just retrieve the Einstein equations. Because you will find that there is 1 over 16 pi g, 8 pi g. You will just retrieve that 1 over 8 pi g times this Einstein tensor plus T mu nu have to go to 0, which is exactly the Einstein equations with my signature. Okay, so you can check. This is just a check on this object. So when you do this exercise, you find the answer. And at the first look, at the first glance, it looks horrible. I will write it anyway because it looks so horrible, and then it becomes so simple immediately. So what you find when you do this exercise is the following form. I will finish just on time. minus V. Actually, to be straight with you, this is probably where I should have started in the very beginning when I talked to you about the cosmological constant, because it's from this energy momentum tensor that you should analyze that you would get to the conclusion that, in fact, a scalar field with zero kinetic term contribution, a scalar field that is just stuck at some point, is a cosmological constant. Now you can see it with this derivation. So a scalar field that's just stuck at some point, all its kinetic terms are 0. And therefore, the only contribution to T mu nu would be positive plus G mu nu V. And V is just a number. And so, or if you want in flat space, it's a constant times eta mu nu. And that's exactly a cosmological constant. So in the flat space limit, that's my last comment today. I'll make 2 comments today. First, when d phi by dx alpha is 0 for any space-time direction, then T mu nu phi is just V of wherever it is you're stuck times G mu nu, which is precisely what the cosmological constant does. So in the flat limit, or comoving frame, we will see this tomorrow, in the flat, in comoving frame, in a sense that I'll define, G mu nu goes to eta mu nu, which is 1 minus 1 minus 1 minus 1. And you see that the energy density of this, T mu nu, goes to V times 1 minus 1 minus 1 minus 1, which we love to call rho minus P minus, or rho P, 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 right? That's how we call an energy momentum tensor in comoving frame. For a homogeneous isotropic system has this form. It has energy density and pressure. You immediately see that the sign of the pressure, rho is V, P is minus V equal minus rho, which is exactly the equation of motion of a cosmological constant. So now you see this. That's the first comment. The second comment I will very quickly show tomorrow before I discuss dynamics is the fact that, in fact, and surprisingly, this T phi mu nu in general, for the classic analysis, is a perfect fluid. And it's a perfect fluid even if the background configuration is not homogeneous isotropic. If the background is homogeneous isotropic, it is obvious the steam mu nu is a perfect fluid, but in general, it is a perfect fluid. So next time, we explain this, we discuss the dynamics, and then we apply everything we have to a model, which is the model of axions. Okay, thanks.
Questions?
Sorry if I don't recall correctly, but yesterday we were at a point where we were discussing the true vacuum sweeping off and electrons passing through, and if this true vacuum bubble sweeps off, and then we sort of started the discussion of finite temperature corrections. So what happened, like what happens to that electron then when it gains?
So you're asking about, so if I understand correctly, the question is about the case where there is a first order phase transition. Mm-hmm. Electron sweeping off means, or passing through means that there is something in space to pass through.
Oh.
So this is not a homogeneous isotropic setup. To my understanding, this is a question for yesterday, which is welcome today also. The question is, suppose you're in the situation that you have false vacuum everywhere and these bubbles of true vacuum because of a first order phase transition, right? And these bubbles are expanding, and some electrons are flying around, and some of them are going to encounter the wall.
Yeah.
That's the question. The answer is that this is a complicated problem, studied in many papers, actually, because it has interesting dynamics. What will be the case if you try to analyze it, you know, a first glance on this problem, you could try to analyze it even classically. Just imagine that I have some particle with mass m, And suppose in the case of electron, the mass m is just y electron times phi over square root of 2 for Yukawa coupling with the field. And now, what this bubble is that now phi is phi of x, which is phi of t and x. This object is really non-trivial, it's expanding. If you take a slice of this field perpendicular to the wall, then you can plot this. You can plot phi. So let's take the slice at a constant time slice also. So it's just a function of r, where r is the spatial distance from the center of the wall. But in reality, remember, this wall is moving, and it could even change a little bit as it is moving. So then inside, the field is close to the true vacuum, maybe doing something. And outside, it is going, let's call it 0. Let's call the false vacuum 0. So you have this profile, and this profile is sweeping through space, really. And so you have a particle with a mass that now explicitly depends on space. And so basically, you have a scattering problem. The particle has some momentum. In principle, your plasma has some excitations. They have some momentum. And so your particle is going to come across this bubble, and it might scatter back, or it might go through and then scatter back a little bit, but it will have some non-trivial interaction. Even at the classical level, it's interesting to solve this trajectory. And there are also quantum effects that you can discuss. This problem was discussed by many. There are things that are different apart from the mass. There can be other things that are different inside and outside. For example, if the model is richer, like the standard model, for example, the Yukawa matrices, Yukawa couplings of the standard model, I'm sure Christoph will talk about it, are actually not just numbers. They are 3x3 complex matrices. And in fact, they contain complex phases, and they contain parameters that violate CP. So it's possible that CP violation will play a role when you do this exercise. Your particle could scatter into another type of particle when it does it. All of these are things that people have looked at in the context of models. So you can have CP violation. People were thinking maybe you can have baryogenesis. Another cute thing that happens for the standard model is that in the false vacuum outside of the standard model, I don't know if Christoph will talk about it or not, but non-perturbative processes related to the large distance structure of the gauge theory, SU2 and SU3, but here what we care about really is the SU2. So there are gauge field configurations that are non-trivial and that are violating baryon number, in fact, non-perturbatively in the standard model. These processes in the symmetric phase where the SU2 is unbroken are happening relatively fast. And you can roughly estimate the rate they're happening, but they're quenched exponentially strongly inside of the true vacuum. So in the symmetry broken phase. And so there can be baryon number violation here, and basically a quenching of baryon number violation at the depth of the bubble, plus CP violation. You can make baryogenesis. You can try to make baryogenesis out of it. So short answer, it's a zoo of interesting phenomena, which is one of the reasons why people were so disappointed maybe when it was discovered that it doesn't happen in the standard model.
So for second order, you have to think about some other aspects then.
Exactly.
Okay. I would like to come discuss later more.
Sure.
Any more questions?
I go. Let me. No, it's okay.
So I was wondering if the effective potential has ever been computed up to 2 loops, because you mentioned something about 3 loops in the standard model.
3 loops was for the 0 temperature potential.
Oh.
The effective final temperature potential was computed at 2 loops. There are some interesting effects there. There is, in fact, a non-perturbative calculation that you need to do at high temperature related to the resummation of what is called hard thermal loops. So there are some infrared divergences related to this effective potential. There are no UV divergences. And for them, you have to resum some of these diagrams. In fact, it's not on the blackboard, but these effects are most important for the cubic term I was discussing before. You have to be very careful about that. So all of this you can find. If you want a nice, very pragmatic kind of practical treatment of that. There is a review by Mariano Quiros that I like. It just gives you the formula, basically, with a very quick derivation. So Mariano Quiros. In my memory, this is from 98 or 99. It does this exercise in different regularization scheme and different gauges. And this is called finite temperature field theory and phase transitions, I think. You can find a lot of stuff in there, including this at least the references for how to do the calculations.
And is this fuzziness problem you mentioned expected to change if we take these computations at more precision levels?
Those computations suggest a more controlled way to deal with this fuzziness problem. I was just giving you an illustration of why you should be cautious about the results that you got. The two-loop effects, in particular this resummation effect, are supposed to tame some of this exercise. Yes, so in a way they are targeting this problem. What really comes out of that analysis, the higher loop analysis, is that in fact perturbation theory breaks down for very small fields. Essentially, whatever you do, you can try to resum and improve it, but the perturbation, there is not anymore small variable to perturb around. And so to really settle the question if we have a first order, second order phase transition in standard model, people did lattice calculations. And I think that is what convinced the crowd that this picture doesn't happen.
All right. Thank you.
Cheers. So, can I? Yeah. I have a quite random question. I'm not sure if I'm even understanding things correctly to pose this question. But a few lectures ago, we were discussing the standard model, two minima model. And I was wondering, so when, let's say, a particle here tunnels to the true minima, in that minima, if we were discussing a Higgs potential, that particle would acquire a lot of mass, right?
But you are right. So I want to clarify this point. Thank you very much. And maybe my demonstration with one-dimensional quantum mechanics is the cause of the confusion. So there is a confusion here. So if what we're talking about when I plot this potential, V as a function of the field, and it has these potentially two minima, what would tunnel from one side to the other is an entire field configuration. This is not a particle tunneling, strictly speaking. So what tunnels is the state of the scalar field on global scales, and the way it would look like is this kind of bubble nucleation. I gave an example in one-dimensional quantum mechanics where you could really realize this kind of traps, and then a particle tunnel. Here, there is not a question of particles that tunnel. Particles would be small excitations of the field near some point.
Right, yeah, sorry, probably misexplained that. But, I mean, once that part of space tunnels, or to that minima, the particles in that bubble acquired a lot of mass, right?
Yes.
And quite a big mass,
yes,
if I remember correctly. So if the region of space is dense enough, is a black hole created?
It's a great question. In fact, you don't need particles to have a black hole, because, great question. What would happen to us if this bubble comes to us? What does this bubble do? It's a wonderful question. Because for us, in that metastable region I was showing before, it's really the case that the remote vacuum is thought to be below us. The minute it's below us, it's negative cosmological constant, because we are essentially zero. This will be whatever, 10 to the minus 30 giga electron volt to the 4. So this is negative cosmological constant. So for us, this question of what electrons will do becomes not very interesting, because in fact what is happening inside of these bubbles are nucleating. You can think about them as bubbles that are nucleating inside of our almost Minkowski space-time, or tiny little bit de Sitter space-time, tiny cosmological constant. They form and expand at the speed of light, if you ask yourself what the metric of space-time does inside the interior of these bubbles, note that the observers inside are causally connected from us. If they send a signal sent by an observer here cannot never reach us because it's competing against the size of the bubble. That's the edge that's moving at the speed of light. So there is a chunk of space here. From the exterior coordinates, from our points of view, it is growing, but it is causally connected from these people inside. These people inside live now in an anti-de Sitter FRW universe, effectively. This discussion is in a beautiful paper by Coleman and De Lucia, which I will finally have an Italian explain to me how to pronounce later. So it's this beautiful paper. What I love about this paper is in the abstract they say what we're calculating is not important. And conclude in the conclusion that, right, it was not important. Nevertheless, it's beautiful and important. And what they find is that they discuss the formation of these bubbles and the behavior of the space-time outside and inside. The space-time outside doesn't even know a bubble is coming because the bubble has net zero energy, like we already discussed, so it doesn't gravitate. If you sit outside, you don't know, and it's coming at the speed of light. So just chunks of space kind of going black. The interior is an ADS space. ADS space inevitably goes to a big crunch. So in fact, what does it mean? It means if you would plot the behavior of now the scale factor, FRW scale factor, let's call it FA interior, the scale factor A of the interior effective FRW metric, this one, even if it was growing initially as a function of FRW time for observers inside, it goes to 0, and it goes to 0 very fast on the natural timescale of the system, which is roughly the size of the negative cosmological constant. So in fact, the interior space goes to 0. What does it mean interior space goes to 0? It means, what does it mean space expanding here? Space expanding here is literally that. There is more space when you wait, right? We look at the coma cluster. You ask how much space there is between us, how many galaxies you can put in there if you wanted. And as you wait, you wait a little bit, the space doubles. The universe expands. ADS, universe diminishes. Coma cluster is coming to you, and it's coming very fast. And in fact, very soon, it will crunch and become a black hole, effectively. It will crunch to, more precisely, it crunches to 0. There is no more space between things, infinite density. So the interior space of these bubbles is null. It crunches to 0. So the volume from the outside expands. The volume from the inside shrinks to nothing. There is nothing here. It's not that there are dead us in here. There is nothing. Okay? So I hope I answered.
Thank you.
So to avoid confusion, all of these fun dances and games that people do with cosmological phase transitions, the reason they can, in principle, be relevant to us is that they're not with the standard model potential. They're imagining to themselves additional scalar fields dimensions to this potential. And the games there are happening higher up, right? So some early phase transition that brought us eventually to that level of the cosmological constant. So there you can tunnel happily. You're effectively tunneling between two expanding DS spaces. And maybe you fill it with radiation when you do it and so on. But that's the point. You do it above. You don't cross the absolute minimum. For us, there is kind of little game to do this anymore in some sense, because we're already so close to 0.
Okay, I guess we are a little bit over time, so let's stop here. Let's thank Kfir again.